Welcome to a summary video of the paper Scale Attachment and Detachment, the role of hydrodynamics and surface morphology. In this video, I will be giving you the main conclusions from our recent paper, so you don't have to read it all. It's the output of a collaboration between multiple departments here at the Technical University of Denmark, and my name is Isaac Abelquist Løe, and I'll be presenting for you today. What is our research about? Well, we have been looking into fouling, and fouling is the formation of material on a phase boundary. So what does that mean? Well, it can be on a liquid and a solid, on a gas and a solid, and on these interfaces, material will deposit and cause havoc. And where do you see it in your everyday life? Well, I've included some pictures here. It could either be on the faucets in your home, where chalk would form, lowering the water output. It could be in arteries where fat would deposit and cause heart attacks, or it could be in ventilation systems where dust would accumulate. So we have been looking at the sub-mode of fouling that's called scaling, which is the precipitation and adherence of inorganic material. So what did we wanted to do? Well, we wanted to investigate the influence of hydrodynamics and surface texture on scaling formation. So we looked at two different flow conditions, laminar, which you see on the top here on the slide, and turbulent, which you see here on the bottom. And then we also tested for smooth and a threaded surface. We used both an experimental and a computational approach, and the computational approach consisted of computational fluid dynamics, which was illustrated by what the images on the slide. This allowed us to understand the transport properties of our system more in depth. So the experimental campaign was performed by injecting two scale-forming solutions into a pipe, taking this pipe to the three-dimensional image center at DTU, and then using a high-resolution X-ray CT scanning to obtain a 3D volume of what was going on inside. And by getting these 3D volume, this allowed us to understand better the mechanisms at play when scale is forming. So what did we see? Well, firstly, I would like to show you just a main conclusion of all the CT scans that were shown here, and that was how much scale is formed. And you see here over here in step 1, then the small crystals is forming in like local clusters, and then they will grow up to become bigger dendrites that are then perturbing out into the flow field, and they will then detach. And this is both the case for the laminar smooth and the laminar threaded case. During turbulent flow, we have another mechanism at play. We see that scale is forming more all over the surface, and then it's growing up to be larger scale. Secondly, a second observation we did was that on the threadings, you see that the fluid is coming in this direction through the pipes, and on the threadings it's the faces that are facing the fluid stream that have the most deposition for both the laminar and the turbulent case. So we wanted to look into these more in depth. So we tried to simulate the material transport across these surfaces. And here I have shown you one of the threadings. And on this threading, you see that down in the valleys, there's a deep blue, and that means that there's not that much material transported there. While on the threading, part of the threading that's facing the fluid stream, there's a very high degree of influx. And this then explains the observation why scale is forming on the front of the threadings. Secondly, we try to investigate how is the flow affected if an obstacle is coming out into the flow path, and we tried to do that both for the laminar and turbulent case. And for the laminar case, we saw that a shadow zone of material influx existed behind these obstacles when they come out into the flow field, which meaning that a little bit downstream of the obstacle, there's no material that's transported towards the surface. And this will again explain the second observation, which was that the clusters were growing more locally. And for the turbulent case, this shadow zone was non-existent, and thereby the whole surface was evenly covered, like a lot of growth material was formed. So here I wanted to show a little bit about how chaotic this system actually is, because you think water through a pipe, that's kind of easy. But when you look at it more in depth, and here we have simulated how material is transported in the system as a function of time, then you see that it's actually a lot of different things going on. So we wanted to look at these more in depth, and we did this by extracting the influx on the bottom, on the middle, and the top of a threading. And these results are shown here on the graph. And what you see is that there is a big periodicity shared between the blue, red, and black line, while the blue and red line, which represents the top and middle part of the threading, they have some lower frequencies that are lost down at the bottom. And this indicates that a higher degree of mixing and also more reaction is taking place on the top of the threadings, indicating why more scale is forming there. So all these observations led us to the following growth mechanisms, and that was based on these two material influx regime. So the first one is the low material influx, and the second one is the high material influx, and they're built up around the same structure, that nucleation on the surface happened, then some detachment of the crystal will occur, and then regrowth on these altered surfaces will then happen. And the difference is that when material is growing on the high influx compared to the low influx regime, then the crystals are formed all over the surface, and when they then grow up, they will be protecting each other from the shear forces from the fluid, and therefore detach much later. So those were our findings. I hope you enjoyed this short video, and if you are interested in hearing more, you can either scan this QR code for the whole article, it's open access, or you can scan this QR code to send us a direct email, or you can just write down on this link. So thank you for watching, and have a great day.